We will continue our lectures on multivariable control. So, in the last lecture we looked at truly multivariable controller design, which included two single input single output controller designs and a design of a decoupler matrix, which made the whole overall design multivariable. And at the end of the lecture I had mentioned that in all the things that we have seen, we have always kind of target a particular input to control a particular output. So, if I have a real multivariable system where I have several inputs and outputs, in everything that we have seen till now we have looked at pairing these inputs and outputs. So, one of the questions that I had not answered till now is, are there approaches to rationally think about how we can do this pairing, is something that we have not talked about till now. So, in this lecture I am going to introduce this idea of relative gain array, which is used to do this pairing. So, you could basically kind of do this pairing and then think about all the other techniques that we have discussed and described in detail till now. In the last lecture on decoupling, we looked at the transfer functions between these various inputs and outputs and then directly use those transfer functions in deriving this decoupling matrices. So, that is the reason why we call this dynamic decoupling, whereas in relative gain array, basically this is kind of the first step in some sense before you actually do all the controller design, because you have to do the pairing if you are going to come up with, let us say 15, 20, 100 single input single output loops that you are going to design and implement. So, in that sense, the less information you use to get a first cut idea of how you should do the pairing, the better. So, in terms of the model that is used for relative gain array, basically we are going to look at only the static gains between inputs and outputs to do this relative gain array, and I will explain all of this presently. So, relative gain array, as we mentioned, is used for pairing the manipulated and controlled variables. So, the basic idea is the following. So, let us again start with the 2 by 2 case and then see how this works. Supposing I have, let us say 2 inputs and 2 outputs. Okay. Now, I can define a gain between each of these inputs and outputs. So, for example, if I give a step input here and this changes and obviously this will also change and I am not changing this. So, this is maintained at 0, then basically I can relate a gain to each of these. So, y1 will be k11 u1, okay, and y2 will be k21 u1. Okay. So, basically what we are saying is, when I just change y1, u2 is still at 0. So, the effect on y1 and y2 can be attributed to u1, and that is basically characterized by a gain. So, y1 is k11 u1 and y2 is k21 u2. Similarly, if I kept, okay, so here u2 is remaining constant, right. Now, if I step u2 up but keep u1 the same, then the change in y1, I will say it is k12 u2, and the change in y2 I will say is k22 u2. So, there are these 4 static gains that you get. Okay. In this case, what we are going to do is basically we are going to look at how we pair this u and y and what is the best pair that we can come up with and so on, by looking at this steady state gains, and I have for this 2 by 2 case I have already defined these 4 steady state gains. However, this experiment that we talked about is in open loop and only one input is changing at a particular time. Now, what we really want to do is the following. So, we want to find what we are going to call as a relative gain, and what is that relative gain? So, a relative gain between a control variable yi and a manipulated variable uj is defined as kij by k prime ij, okay, and we will do this definition. Kij is the open loop gain between yi and uj, which is what we saw here. So, if you talk about this open loop gains, there are 4 open loop gains between y1 and u1, y2 and u1, y1 and u2, y2 and u2. So, there are these 4 gains. Now, what we want to do is, now if I change u1, I know this is the gain, right, but this is an open loop. Supposing I were to close the other loop, okay, that is, I already have a controller in place between y2 and u2. Now, if I change u1, what will happen to y1 is an interesting question to ask, right. Would the same gain be there, or will the gain be different? Now, since we basically do all our designs, remember control designs based on these open loop transfer functions, we are really looking at how much you will change y and then designing a controller. But in a multivariable case, whenever u1 changes, it does not mean that the u2 is not changing at all. So, the problem is when I have a particular gain or a particular process model which is an open loop transfer function between u1 and y1, and I design a controller, it is not reflecting the reality in a closed loop where both u1 and u2 are changing. So, what I want to do is I want to find out the effect of closing the other loop on say u1 y1 loop. So, basically what that means is I am going to define something which is the gain between yi and uj when all the other loops are closed and deliver perfect control. So, we will understand what this means. So, this is an important word. Okay. So, basically all we are saying is, so typically in open loop I would have had this k11 u1. Now, in closed loop I am going to have something else which I am going to call as k11 prime u1, and this becomes a prime because of the effect of the other inputs. You can also kind of think about this now that we have been doing this for long enough. So, we should start kind of making connections and start thinking about these in slightly more sophisticated ways. Remember in the decoupler, when you had u1 decoupled transfer function with y1 and u2 decoupled transfer function with y2, the model, if it were just u1 it would have been g11, but the minute we made it u1 decoupled it was g11 minus other terms, right. The other terms come from the interaction of the other loop, right. So, in some sense the model itself changes when you look at things in open loop and closed loop. That was a dynamic version of this. This is a very simple static version of this, where we are saying if I had kept both loops open and then simply gave a step in u1, what would be the gain I will get, which is k11. Now, I want to contrast that with what will happen when I close the other loop, in which case what I am saying is somehow I have to define what closing the other loop means. So, I am going to say closing the other loops means that the other loop is doing perfect control, okay, whatever it needs to do it is doing. If the other loop is doing perfect control, how much of that perfection is going to affect my current loop is the question that we are asking, and that change as reflected in the gain is this k11 prime u1. So, this is the basic idea, and the relative gain for this will be k11 by k11 prime. Now, the other relative gain, supposing you were to take the gain between 1 and 2, then y1 is k12 u2, and similarly once now if I close the u1 loop, the gain I will get will be k12 prime u2, okay, and so on. So, you can do this for all possible combinations, which will be 4 in this case, y1 u1, y1 u2, y2 u1, y2 u2. Okay. So, you will get these 4 modified gains. Now, the relative gain is basically the ratio of this gain in open loop and the gain that will result if the other loops are closed and perfect control. Okay. So, that is the basic idea, and the ideal situation is when I simply have relative gain as 1, right, because that means both gains are the same, in which case whatever I see in open loop I will get the same performance even when I close all the other loops and make them perfect control. So, the other loops are not going to have any effect. Okay. So, that will be the ideal situation, but in reality that is not going to happen. Okay. Now, you will notice that when we do this computation, it will be very similar to your dynamic decoupling. So, I would really encourage you to go and look back at that lecture and then see how some of these ideas are quite similar. Okay. So, now let us look at these equations here. So, at steady state we are going to derive this relative gain array for a 2 by 2 case, very simple, and then can easily extend that to 3 by 3 case and so on. So, at steady state, if I were basically in open loop, then and I change both, let us say u1 and u2. So, these are the kinds of equations that you will get, and then we will describe what perfect control for the other loop means, and then we will show you how to derive this relative gain array. So, I have a, let us say, change in u1, change in u2. So, I can write y1, this is basically now static models that we are writing. Okay. This is, you can think of this as the ultimate effect of u1 and u2 changes on y1 and y2. That is the reason why we are using only the gain, and as I mentioned before, the reason why we are using only the gain is because we want to use as little information as possible right at the beginning, so that we can do pairing, and once we do pairing, whatever decisions we have made, we will live with those and then correct for the other things through the many techniques that we have talked to till now. So, ultimately if u1 and u2 have taken certain values, then I am going to have y1 is k11 u1 plus k12 u2, and y2 is k21 u1 plus k22 u2. Okay. Now, what I want to do is that I want to, let us say, compute the relative gain array for the gain between y1 and let us say u1. So, first what I am going to do, since I am looking at y1 and u1, the other loop becomes y2 and u2, and if the other loop has perfect control, we are talking about from a disturbance rejection viewpoint here, we are not talking about changing set points and so on. So, when we talk about perfect control for the other loop, that means y2 would have been initially having a value of 0, and perfect control means it should stay at 0. So, what we are going to do is we are going to set the second equation to 0. So, that is how this notion of the other loop is delivering perfect control comes into picture. So, since we are delivering perfect control, y2 is not changing from its value at all, right. So, in which case I will get 0 is k21 u1 plus k22 u2. From this you can get u2 is minus k21 by k22 u1. So, this is the equation you get. Now, what you do is you now substitute this equation back into this for u2. Okay. So, you substitute this equation for u2, then you will see that you can do some simple manipulation. Now, you see this here. Okay. So, which gives you k prime 1 1 1 1 1, which is basically the relative gain when the other loop is closed and perfect. And just like dynamic decoupling, you will notice that initially it would have just been k11 if you are just looking at u1, but because we want to bring in the effect of the other loop through perfect control of the other loop, there is another additional term that comes out. So, basically what this says is if the other loop was closed, you will see this relationship between y1 and u1. So, I can think of this as the gain between y1 and u1 when the other loop is closed and perfect. So, the relative gain between y1 and u1 is k11 divided by k prime 1 1. So, which is basically k11 divided by this right here, and if you just multiply this k22 and take it up, you will get this expression here. So, these are simple algebraic manipulations that you can quite easily follow through, very simple. And again, like I said before, since you have been taking this course for so many lectures, it is time to kind of go and consolidate all your understanding through the connections between these various concepts. You will see how this is very close to the dynamic decoupling idea, except that we are working with only static gains. Now, this was done only between y1 and u1, this relative gain. You can do a relative gain between y1 and u2, y2 and u1, and y2 and u2. I leave this as an exercise for you to basically look through these various transfer functions and do these computations for the other things, so that it's easy for you to understand this. Now, this, so basically there will be a relative gain 1 between y1 and u1. there will be a relative gain, let us say, so we can call this as 1 1 because it has been 1 and 1. So, you will have a relative gain 1 2 between y1 and u2, you will have a relative gain 2 1 between y2 and u1 and relative gain 2 2 between y2 and u2. Now, the formula here is the following. So, you need a little bit of matrix algebra to understand this. So, let me explain this. So, you can actually go ahead and do this for all the 4 and actually check this result. We will leave that as an exercise for you. Basically, if I want to get the relative gains, okay, so what I do is I start with the standard gains, which is k11, k12, k21, k22. So, if I have y1 and y2, the standard gain matrix k will be k11, k12, k21, k22 multiplied by u1 and u2. So, if you call this as the k matrix, then the relative gain matrix, which is RG11, RG12, RG21, RG22 is k dot. So, I will explain what this dot means, k inverse transpose, right. Now, once I have a k matrix, k inverse is easy to compute, okay, and the transpose of that is also easy to compute. So, the only thing I have to explain is what is this dot k inverse transpose means. This is not your standard matrix multiplication. Now, if I have two matrices, let us say A, B, C, D and E, F, G, H. Now, if I do a standard multiplication between these two, then the first element here will be A, E plus B, G and so on. So, which is what you have learned from high school and so on. Now, there is called this dot operation, which is an element wise multiplication. Now, what that is very simple. If it is A, B, C, D dot E, F, G, H, then what you do is you simply multiply element by element. So, the first element of this operation will be A, E, this will be B, F, this will be C, G and this will be D, H. So, this is the element by element multiplication. So, basically it is different from the standard matrix multiplication. Okay. So, if you want to compute the relative gain array, all you need to do is get the gain matrix, do an inverse of that, take a transpose of that and then do a k dot this matrix where this dot represents element by element. So, if it is A, B, C, D, E, F, G, H, the first element is A times E, this element is B times F, this element is C times G and this element is D times H. Okay. So, that if you do, you will get this. The nice thing about this is this kind of generalizes this to any size. So, if it is 3 by 3, again it is same k dot k inverse transpose, except that the k matrix will be a 3 by 3 matrix. Similarly, if it is 4 by 4, k will be a 4 by 4 matrix and so on. In fact, it will be worthwhile for you to actually do this computation for 2 by 2 to see these results match. Now, that we know how to compute this relative gain array, can we interpret the relative gain array? Now, as I said before, relative gain array is 1 is the best situation, because what it says is relative gain, remember, is the ratio between open loop gain divided by gain which takes into account the effect of the other loops on the open loop gain, right. Now, if that gain also turns out to be the same as the open loop gain, then basically what it says is we really do not have to worry about closing the other loops when we design a controller for this pair, because closing the other loops does not have any effect on the overall gain anyway. So, you do not have to worry about it, right. So, that is the best case. If you set that relative gain 1 1 term to 0 and see what is the effect of this, then basically it says the interaction term should go to 0. So, there should be no interaction, only then you will get perfect 1. If there is slight interaction, you will not get 1. But just as a limiting case that you understand that relative gain 1 is the best, and that will come out if you have 0 interaction. Now, if the relative gain is much greater than 1, okay. So, then what does this mean? Which basically means the denominator which I have here, the denominator should be quite small. That basically says that the interaction terms dominate, okay. So, that basically says that if I had a open loop gain and the denominator term becomes very small. So, I assume that when I make a certain amount of change in u1, I will get a certain amount of change in y1, but that will happen in the open loop, but once I close the loop, since the denominator has the gain once other loops are closed, it says that since the denominator is 0, the actual effect u1 will have on y1 will be much less than what I thought of before, because once I close the other loops, those effects come and reduce my overall forward effect, is what it says. Okay. So, in other words, basically if you design a controller based on this pairing using a open loop transfer function, then you are going to be very optimistic in the sense that, oh, if I make this change in u1, there is going to be this amount of change in y1, which will be true in the open loop case, and you would have designed your controller based on that. But once the interaction effects kick in, when all the other loops are closed, then what is going to happen is whatever change you expect for a change in u1 while you design the controller is not going to be realized in the multivariable control sense. So, once you close all the other loops, the gain is going to be very low. So, if you choose this, it is not going to be a good idea, because you cannot do a good design based on the open loop gain. Now, if the relative gain is very small, that means the opposite, right. So, I have an open loop gain on the top, and then when I close the other loops, the gain becomes much larger than this. That is the reason why that ratio becomes small. So, what this says is something interesting. It says if you paired this input to the output, you get a particular gain, but when I close the other loops, right. So, that means u2 and u3 and u4 are all changing, and those changes are inducing much bigger changes in y1. That is the reason why this ratio becomes small. So, this gain, which is because of change in u1, is much less than the change in y1 that occurs because of closing u2, u3 and so on. That means u2, u3 and other things seem to have bigger effect on y1 than the u1 that you have chosen for this. So, that basically means maybe these other secondary manipulated variables which you did not choose for this are better for this, because they seem to induce much bigger changes in y1 than what you have chosen. So, again very small relative gain is not a good idea to have. Now, the negative relative gain, if you have, that is a real problem, because what it says is in open loop, if you think, let us say when I change u1, y1 increase, but actually when you close all the other loops, it says that if you increase y1, u1 will actually decrease. So, imagine all the pandemonium or the confusion that will result if you actually tune assuming that increase in u1 will increase y1, whereas when all other loops are closed, it actually decreases y1. So, this can create all kinds of problems leading to instability. So, the key idea is that 1 is the best, right, negative you really do not want, very small is not good, because basically that says the other loops have a lot more effect than your control variable than the manipulated variable you have chosen. So, this is not good. Very large is also not good, we said, because the interaction effects are so much that they are actually going to bring down this gain quite a bit. So, the best is to go with something around 1 or larger, okay. Smaller is a bigger problem. So, anything below 0.5 you avoid, and then you try to choose things which are close to 1, 1 is ideal, you might not get that, or slightly larger than 1 is also okay. So, this is the general rule of thumb for relative gain array, right. So, now let us take a very simple example to do this. Supposing you had, let us say, the gains like this: y1 is 10 u1 minus 6 u2, y2 is 10 u1 plus 18 u2. That means the steady state gain matrix is this. A relative gain array is k dot k inverse transpose. So, if you take this k, you can do this computation by hand or by software that you use for analyzing control systems, and then you will get a relative gain array of this. Now, let us try and interpret what kind of pairing we should do. So, the relative gain between y1 and u1 is 0.75 and y1 u2 is 0.25. y2 and u1 is 0.25 and y2 and u2 is 0.75. So, in this case, remember we said we want to avoid everything less than 0.5 and we want to be as close to 1, slightly lower or slightly larger is okay. So, in this case it is very clear cut. So, we know that y1 should be paired with and y2 should be paired with u2. So, in this case it is very simple, the pairing rule for this example. Now, let us take one more example, which is a 3 by 3 system to let you understand this better. So, 3 by 3 again I have a gain matrix, which is this. Now, you do the same relative gain computation here, then you get this matrix here. So, this is row is for y1, this is for y2 and this is for y3 and this is for u1, this is for u2, u3. So, if you notice, when I look at y1 row, the one that is the best is u3, which is as close to 1 as possible. So, I will pair y1 and u3 is one pair. So, that basically means when I design my controller, CISO controllers, I will use u3 as a manipulated variable for y1. And clearly when you look at y2, we want to avoid negatives. So, basically y2 will be paired with u1, and then when you look at this here, you will notice we want to avoid negative, we want to avoid less than 0.5. So, the best choice in this case is y3 will be paired with u2. So, this is how you look at the relative gain array to do the pairing, and once you do this pairing, then you go ahead and then do your CISO control loop design for 3 single input single output loops, where u3 is paired with y1, u2 is paired with u1, y2 are paired and u2, y3 are. Now, once you do the pairing, you can directly go ahead and then do single input single output control design, or you could use dynamic decoupler with these choices and so on. So, you can do all kinds of things once you have chosen a basic control structure that you are going to use. So, with this we have completed the traditional multivariable or traditional advanced control ideas that we use. In the next lecture, we are going to start really looking at optimization based controller, which is the most modern controller that is used. In fact, I would go as much as saying that almost most of the multivariable or more advanced control implementations in industry are model predictive controllers, and this notion of model predictive control and model predictive controllers is going to become more and more popular, because solving online optimization problems is becoming more and more efficient, and we can include constraints and all kinds of advantages are there when we use model predictive controllers. Now, model predictive controllers by themselves are a very large subject area. However, I think it is very important even at an undergrad control level to start understanding what model predictive controllers are. So, to be able to teach model predictive controllers, what I am going to do is I am going to basically talk about the concept and then show a formulation for a single input single output control system, how you would formulate a model predictive controller for that, and then I will point out how the multivariable model predictive controller design is trivially extended from a single input single output multivariable single input single output model predictive controller framework. Just so that we understand this, as I said before, there is a lot of literature and lots of exciting work that has happened and that is happening in the space of model predictive controllers. So, these lectures, the 4 or 5 lectures that I will give on model predictive control are largely introductory, but I hope that will give you the tools and understanding you need to start reading the more advanced versions of model predictive controller. Nonetheless, I think it is a good idea to introduce this idea or this concept at the undergrad control level. So, I will see you next class with a series of lectures on model predictive controller. Thank you.